All right, continuing on with class 13. This is a more useful example, I think. It's quite a bit longer. It starts some stuff that we're going to be doing a lot. All right, it's just this right here. Really, we're just concentrating on the conservation of mass, but we could also use this for the conservation of energy. As an example. So we have a boiler that receives a constant flow of 5,000 kilograms per hour. And I wasn't sure that H was, I usually go HR for hours. Liquid water at 5 megapascals, 5,000 kilopascals, and 20 degrees Celsius. And it heats the flow that's what boilers do, such that the exit state is 400 degrees Celsius with a pressure of 400 megapascals. Always found that interesting, but there has to be a pressure drop, right? It will only flow from a high pressure to a low pressure. Determine the necessary minimum pipe flow area in both inlet and exit pipes if there should be no velocities larger than 20 meters per second. This is actually, we're kind of starting to become designers from this. And I would actually pick the diameter instead of just picking the flow area. So that's what I'll do. So anyway, I'm going to start by fixing some units there because I don't know why we're going with kilograms per hour. We divide through by 3,600 and get 1.389 kilograms per second, right? We're dealing with meters per second. We might as well go kilograms per second. P1 is equal to 5,000 kPa. T1 is equal to 20 degrees Celsius. And of course, this is water. It's very compressed water. This right here should be steam. We don't know if it's superheated or not. And T2 is equal to 450 degrees Celsius. So the best way to approach compressed water is first to double check that it's compressed water. I mean, you could look in table B.1.1 or 0.2, excuse me, this the pressure based indexed one, and at P equals 5,000 kPa, you can see that the temperature, the saturation temperature, is going to be 264 degrees Celsius. So obviously we are not steam yet. This is subcooled, if you will. And so what I would just do from this is I'd probably use the V at that, right? The fluid specific volume. And that comes out to 0.00100, and I think there's a number after that, but I'm not sure. But anyway, I just went ahead and used it, right? So in the previous example, I think I also mentioned that's just really a good assumption to make. It's you're not being off too far. Something I'll do at the end of this, which I'll answer something that's not quite being asked, but I'll do it anyway. Let me get the fluid enthalpy coming in. Right. So this is actually from the next stuff that we will be doing in the next class and be doing a lot of, but we would almost always want to get the enthalpy in something like here. Also, let's see. I wrote this over here. I don't know why. I'll go back over here for table B.1.3 and look up at P2 4,000 kPa and at T2 450 degrees Celsius, we will see that we are in fact 4,000. Oh, I see. I know what I went and did this. I think I got these were actually from table B.1.4. Yeah, that's where I got those. B.1.4. So that I think that is the value that they had in both of these things. But we could have gone to, and I don't think this is true right there. Then the V, those are not true because it was from this table right in there. But a lot of times you can just go to the saturated table and you can pick up the liquid and get what it is for there. This is probably not as true, but this one is a good assumption. All right, so I guess here is the table 1.2. No, okay, I'll just go to this one right here. Yeah, we find out that this is these values are in this table, so we're able to get that the specific volume afterwards is 0.08003 after it's been heated up by the boiler. And its enthalpy, which we didn't need for this actual problem, is 3,330.23 kilojoules per kilogram. All right, so anything else we want to do about that? No, I don't think so. All right, so let's take a look at what this thing is actually doing. It's always a good idea to draw the box. So anyway, this thing is like, a boiler is just a type of heat exchanger. We are often burning some fuel inside the thing, or maybe we're capturing some gases that are blowing through here. If it's some type of recovery, so we have an M dot, and so here's state 1 and here's state 2. If we're looking at the fluid, the water that's being heated up right there. So here is our conditions at state 1. We'll call this 1, and here's our conditions at state 2. For this problem, they're focused on the minimum pipe flow area if there should be no velocities at 20 meters per second. So the equation that we're really looking at is an M dot equal to V times A divided by specific volume. I actually kind of prefer this equation right here. That makes me feel a little bit more. No, didn't mean that. That should not have a cross across it right there. Sorry. Yeah, right there. Because this right here is the volumetric flow rate, and I usually like to have the density. But it's because we use specific volume so much, we'll stick with this one right here. So we know the mass flow rate. So what we really want to find is what the required area is. For state 1, I'll write state 1 here. We'll have this area is going to be equal to M dot specific volume over velocity. So this would be 1, 1, and 1. And we're limited, so we're told that this can't be 20 meters per second. So we need to have at least an area that's equal to what we're about to find. So we have our 1.389, and that's going to be kilograms per second. And we multiply that by 0.00100 cubic meters per kilogram. And we divide it by 20 meters per second. And what that's going to do, let's see, that's going to get rid of our seconds. It gets rid of kilograms. And it gets rid of one of the 3 here. So we're left with meters squared. So we're cool with that. So the area 1 is going to be really small number. I thought it was like, well, that's really tiny. And these are going to be meters squared. Now, I'm trying to get my head wrapped around that. I don't know. I would rather find the diameter. And so we know that this is equal to pi over 4 d squared. So we could find what d is. We just take the square root of the of 4 times the area divided by pi. And if we do that right here, we end up with 0.09404 meters. And so this is D1. Wow, I really messed that up. D1, I'm tired, I want to go home, is 9.40 millimeters. That's tiny. That's nuts. It's like a centimeter right there, right? Of course, you wouldn't design it. You'd make it 10. You would make it 10 millimeters. You would go up to the next size. That's what I would choose, right? Which is just going to be, here you go. I couldn't get it right here. That's going to be that size of an inside diameter. That's just tiny. But anyway, so coming back to whatever the other one, because they wanted both the inlet and the outlet. So at state 2, we would do the same thing. A2 is going to be m dot over V2 over V, which was going to be whatever it was going to be, right? It's going to be 20. So we got the same 1.389. We're confident with our units canceling out. And now we're going to use the specific volume here of, it's going to be steam, and divided by 20. And we get a larger number for this one, but still kind of small, I think. It ends up being 5.558 E minus 3, but I would want to find the diameter here, where we have, so we have the square root of 4 times A2 over pi. And that gets something a little bit more reasonable. Still not very big, but 8412 meters, which is 84.12 millimeters. And so I would pick 85 if we were doing the design of the thing, right? So it's kind of an even increment. Actually, pipes come in certain sizes, so you would look up and see what their actual inside diameter would be. One last thing. All right, so this is what the problem was meant in the book, and this is one of the one of the problems in Borgnakke chapter 4. I picked one out because I wanted a better example than the ones that were in the that were contained in the book. This problem right here, of course, we're not in that section yet, but I kind of think we should have be, where we take a look at the amount of energy that got put into this water, turning it into steam. So I'm missing my clipboard. No, it's right here. With my extra paper, I don't know if anybody's watching these videos. I don't know how much useful this is. Looking at this thing right here, we would want to use our first law. I mean, that was the point of the whole spiel into this section. I guess I'm waiting for the next thing. But anyway, we would say, well, if the control volume, this doesn't accumulate anything, so we're going to leave that as 0, which is, pretty well true. And we're going to have that flow coming in and work going out is what we usually expect. And then we'll have plus m dot h coming in minus m dot h coming out. Well, there's no work involved in this to be extracted or to be put into, so that's going to be 0. So we're basically going to say the heat flow is going to be equal to, and we're going to bring these guys onto the other side over there, and we'll go m dot times output minus input, and so we can have our values. So we get 1.389, and these are kilograms per second, and then we have our enthalpies, right? So the outlet enthalpy was 3,330. Input was 88.64. So 3,330 point, way too many details, but 23. Okay, I don't need that many sig figs. 88.64. and you multiply these out. And remember, these are kilojoules. So if they were, we would work the thing out and find that we would have, these are actually 1,000. So the answer when you're doing this, kilograms per second multiplied by a kilojoule per kilogram, you get kilojoules per second, which is a kilowatt. So we get 4,000. Is that true? Let me think about that. Let me think about that for a second. Kilojoules per kilogram. So what I wrote down on my page doesn't sound right. No, now I'm starting to second guess myself. 4,503. And these should be kilojoules per kilogram. So this would be kilojoules per second, which should be, kilowatts. 4,503 kilowatts, unless I'm losing my mind. I feel like I'm losing my mind. This seems like a whole lot. I don't like it. I want to say that these are watts, but they're kilojoules per kilogram. Keep repeating yourself, dude. And a joule per second. Yeah, I think that has to be right. Okay. Well, you can contradict me in the comments, please. Tell me I'm wrong if I got that wrong.